Andrew, what did you want to talk about?
The two questions from the exam two.
Okay.
Read it to you if you'd like.
I would like very much, because I don't know.
The first one was is a transformation from the space V to W, with H being the subset and the subspace of V. Is that a transformation that takes elements from that subspace to the other vector space, subspace?
A subspace, yeah. Can I borrow that? Okay. Okay. Yeah. So we have a linear transformation from one vector space to the other. The fact that it's a linear transformation is the key point in this. So H is this is a subset of this symbol. These symbols right here mean that it's a subset. A subspace is stronger than that. So we're assuming that it is a subspace. And we use this notation. This is not a made-up notation, it's a standard. So T of H is all of the things in W. So let's say W, big W, such that W is the transformation of something in H. So we have a subspace of V. I can draw a picture. A lot of people drew a picture to prove this. It's not a proof. Definitely not a proof. So here's V. Here's W. And there's a linear transformation that goes from V to W. H is a subset, which is also a subspace. So I'm gonna write the zero vector of V inside of H. And then over here we have T of H. So this is the So this is kind of getting carried over. This whole subset, what is the image of this under that transformation? And what we're trying to show is that this preserves the subspace stuff, right? That it has to meet certain qualifications in order to be called a subspace. And we want to see that this thing over here satisfies those qualifications as well. So, let's see, do we remember what all of the qualifications are for being a subspace? You have here contains zero.
Close under addition.
Close under addition and close under. So, contains zero. Addition. The only kind of multiplication that we have access to in a vector space, which is scalar multiplication. We don't have a kind of ordinary multiplication. We have a multiplication by a specific set of things. Okay, so these were a subset of, well, these were a few of the requirements that something had to meet in order to be considered a vector space. There's a set of things. It has an addition and multiplication. It satisfies all of these rules, commutative, distributive rules, all of this other stuff, right? Whenever we look at this as being a subset of a vector space, it inherits all of that stuff automatically. The only things that it doesn't inherit by virtue of being a subspace is that these three rules right here. So that's all we have to check in order to see that a subset of a vector space is a subspace. Oh, I should probably write T of this. It's a subset. This little line down here means it could possibly be the whole set. We're not distinguishing between the possibility that it's a subset and a proper subset. Okay, so we gotta just check these rules. T of 0 is equal to 0. Is this true? Oh, first, let me say. What has to be true in order for T of H to contain 0? So 0 belongs to T of H if and only if 0 equals T of H for some H. I'm writing out all of the reasoning right now. It's not necessary to be this specific. You know, a lot of this is implicit. You know what this means. But for this first example, I think it'll be helpful. So we want to show that 0 is in T of H. This is the same thing as showing that 0 equals T of little h for something in here. There's something that goes to 0. And we can examine this by looking at T of 0 equals 0. Why? A lot of people just simply said T of 0 is equal to 0 without giving any explanation of why that's true. So why is this true?
Is it because it's a linear transformation?
It is because it's a linear transformation, that's right. But what is it about a linear transformation that makes that true? What's the definition of a linear transformation?
I'm thinking of the thing where it's like T of H1 plus T of H2 equals T of H1 plus H2.
I'm gonna, there's more to, there's slightly more to it. I'm gonna condense all of that down into one statement. So T of A, V plus B, U equals, okay, A and B here are scalars, and U and V are vectors in our codomain, our domain, sorry. So these are vectors in our domain, and these are scalars, and so we look at any linear transformation of things in the vector space. So the transformation, if it, in order for it to be a linear transformation, it has to commute with them. In other words, this is equal to AT of V plus BT of U. This has the consequence that in order to figure out what the transformation of any element is, we only need to know what the transformation of basis elements for that space what those transformations are. And so we can reconstruct anything from those basis elements. We can reconstruct its transformation from the same linear combination. So that's what makes it a linear transformation. So I want to exploit this somehow to get this. And the way that I'll do it is to say T of 0 times U. U is just arbitrary. I actually don't care what U is. This is equal to 0 times T of U, and the dot here, I mean scalar multiplication. This dot is not in any way related to the dot product. This is a scalar. So this is 0 times T of U, which is 0, because 0 times anything is 0 in the vector spaces. And over here, 0 times anything is 0, so this is T of the 0. And just to remind me, now I'm talking about the 0 vector. This is the 0 vector in different spaces. it's a common thing, we have, every vector space has a zero vector, and, so this space here has a zero vector, this space has a zero vector, but they're not the same thing. These may not necessarily be the same space, and so the zero vectors this may be an element in V and this is an element in W, but we kind of mentally conflate them and just think because every space has this special zero vector, we're just going to call it the zero vector and, save a lot of elaboration that I'm doing right now. Just for the sake of clarity, just for the sake of mental clarity about what these things are and how we deal with them. So that shows that zero is in here. So we've got that. Closed-under addition works in a very similar way. We need to show that if we have two elements in T of H, then their sum is also in T of H. And so if we have X and Y belonging to T of H, then we have T of U and T of V that are equal to these things. For some U and V and H, should have called them like H1 and H2 or something. Okay, so we want to say what the sum of these things is equal to. The sum is equal to T of U plus T of V. Mentally translating this maybe to H1 and H2. You like that better? And by linearity, this is T of U plus V. And this belongs to T of H because U plus V belongs to H. This U and V is a subspace, or H is a subspace. So H is closed under addition scalable. Okay, now we've got this one. We do the exact same thing here, except instead of writing plus, we write scalar multiplication, and it commutes with the linear transformation the exact way that you explained it. So that's how we do it. Now, what I would have settled for is something much. This would have been fine, just that right there. All of this is kind of implicit in this. That would have been good enough. But, yeah, that's what it takes to show that it's a subspace. We come to something at the end of this. We have this nice conclusion, which is that linear transformations preserve subspaceness. I coined a word there. The property of being a subspace, linear transformations preserve that. So that's one of the many special things about it. Okay, what was next?
It was on the other page.
Okay, I'll give it back to you.
So let X having B two elements and let f of X be the set of all the rebellion functions.
Yeah, this was a, in case you can't tell, this is a question of my making.
Oh.
So this was largely conceptual, almost completely conceptual. So let me write this out. We start with a set AB. Okay, this is just a set with two arbitrary elements. I've named one of them A and I've named the other one B. These two elements could be 1 and 2, or -1 and 1, or infinity and 0. I don't care. Square and circle, right? In fact, this was going to be square and triangle. To emphasize the fact that it really does not matter what the names are. It's just important that there's two of them. Okay, f of x, or f sub x, sorry. This This is going to be the set of all real valued functions on X. So that's the English language description, and then I say all functions with X as their domain, and R as their, I say range, I should have said codomain. So this is the set of all functions that go from X to R. And we had decided that any set of this type can be made into a vector space. So let's say that we have two functions. Oh, first, what is this set? What is it a set of? What are the elements in this set? What are the things inside the bag? Right? They are functions. The functions take in square and triangle and output f of square and f of triangle. Some real number is assigned to the square and some real number is assigned to the triangle. And so this set is all possible functions. Everything that's possibly a function. And so if I have two things from this set, this was what we agreed upon, and I have, let's say, some scalar. So I want to show that I have scalar, I have vector addition and scalar multiplication, and that makes it a subspace, or that makes it a space. So f plus g should be a function, and so the way we define this function is f of g of square, for example, is equal to f of square plus g of square. So whatever real number I get out for square from f, and whatever real number I get out when I put in square into g, defines what this will be at square, and similarly at triangle. Right? And so this completely defines the function. That is 100% of what the function is. The function is something that has a value at square and has a value at triangle, and this is how we compute the value at triangle, and this is how we compute the value at square. Okay? So this is a new function that is a real value function on x, and so it's inside this set. So f plus g is inside f x. Right? Scalar multiplication works the same way. AF squared, where now I think of AF as a vector, something, looking at this through the lens of that being a vector space. It has a scalar multiplication. How do I define the scalar multiplication? Exactly as you might expect. I take the value of f at square and I output a times that much. And so we also get scalar multiplication in this vector space. So the number one thing that I was looking for as I looked at the answers to this and my expectation sank lower and lower and lower, was first of all, does your answer demonstrate that you know what f sub x is? This is a set of functions. So however you choose to define the function is totally fine, it doesn't matter. So long as you are showing that this thing is a function, and got a wide variety of things that would not do that.
I think it was asking for a basis though, right?
So it's asking for a basis of this vector space, right? A basis is just a certain number of things out of this vector space, that everything can be built out of linear combinations of them. Okay. So in order to get two things from this space, I first of all wanted to see, I would have liked to have seen from everyone. What anything from this is, anything from this set is a function. It's one of these functions. And so demonstrating a function of any kind, we've got some points. And how can you define a function in a variety of ways, but one way is to say what f of squared is equal to and f of triangle is equal to. And this gives me all the information. This is a definition of the function, right? It's just as good as saying f of x equals x squared. This is good enough to tell me what this function is. It's a function that takes in an x and spits out an x squared. And so long as I know what the domain and codomain of this function are supposed to be, I'm okay. All real numbers? All real numbers? I'm great. Okay, so how do we get a basis for this? Well, let's take an arbitrary element from this and examine it. An arbitrary element from this is a function. Let's just use this space right here. It outputs some real number at square and some real number at triangle. So I'm going to call this one A and this one B. Doesn't matter what they are. Now I'm going to pick two special elements from this, two specific elements. This is the general element, right? This is any function. Any function is defined just by these two numbers. Okay, so there's any function is defined by these two numbers. Now I want to pull two specific things out of here that I can combine together in order to get this. So I'm going to say this is just a convenient choice. It's not the only choice, but it's a convenient one. B1 is equal to, let's say, B1 such that B1 of square is equal to 1, and B1 of triangle is equal to 0. And B2 such that B2 of square is equal to 0, and B2 of triangle is equal to 1. And now, how do I combine these two things together in order to get F? Well, this is going to output 1 x squared, and I want this thing to output A, so I just multiply this by B1, and I notice that this doesn't affect at all how it outputs at triangle, right? This is going to output 0 at triangle. I'm not quite finished yet. Now this one outputs 0 at square, so it's not going to mess up what this thing does at square. And it outputs 1 at triangle. And I probably should have named them B1 and B2, but here we go. And that's it, right? Now I can write any f belonging to f sub x as a linear combination of B1, B2. I need to do a little bit more work to show that I can't write it as a linear combination of just B1 and a linear combination of just B2. And so this is the smallest possible set that has this as its span, and therefore it would be basis. But in order to get to this area over here, I first have to know what it is I'm dealing with. And that was the key thing right there. This example, this was one of the examples that we had for vector spaces that weren't just Rn for some n. So yeah. Now notice that because the basis was two elements, this is a two-dimensional space, and in fact, it's the scalars, the set of scalars, the field of scalars, it's the real numbers, and so it's a two-dimensional real space. So we do have that f of x is isomorphic to R2, and there's a translation between these two things. So it's isomorphic to R2, and that's one of the big, if you don't often deal with infinite dimensional vector spaces. So for example, if instead of square and triangle, we had triangle, square, pentagon, hexagon, and so on, right? 3, 4, 5, 6, and so on. If we had infinitely many things right here, then we would not be dealing with a finite dimensional vector space. It takes a little thinking to figure that out, but it's not too much. So you see that this isn't a finite dimensional vector space, and things become a lot more complicated. One of the big results of this class was that any finite dimensional vector space is isomorphic to Rn, and so really for all finite dimensional vector spaces, no matter what they are, no matter how they're structured, this is a particularly strange one, right? With these shapes and then they're attached to real numbers somehow. This is a particularly strange one, but it's still basically just R2 in disguise. And the fact that we can take any finite dimensional vector space and just turn it into R2, and take any linear transformation and turn it into a matrix, no matter how bizarre looking it is, as long as it's finite dimensional, it's really just Rn and matrices, and that's it. So that's one of the really big results of this class, and you don't get a sense for how big it is because we only deal with finite dimensional vector spaces, so big deal, right? We don't see any examples of infinite dimensional vector spaces, so who cares if it's, who cares how convenient and amazing that is? Okay, what else should we talk about?
I did have a question about the exam a little bit. So did you decide if it was going to be like a doable length or pick which question you want to answer?
They're all doable lengths.
Okay.
Depends on what you're trying to do. So it's going to be, in my opinion, about twice as long as exam 3, plus a little bit. So it's just slightly longer than exam 3. Some people left early, so clearly it wasn't long enough. So yeah, that's going to be about what it's like.
Okay, and okay. And the other question I had was stuff like
Changes nothing about how you should study for the exam. You should study everything.
No. I was curious. And stuff like Kramer's rule that doesn't make it on the exam too. Like, do we worry about that? Like that was like a very just computation, memorize the formula thing. Do we memorize the formula or since we?
I will say that. Okay, two things. First, if you're memorizing a formula, I don't consider that to be a lot of mental work, right? So it's a small amount. You memorize the formula if you want to memorize it, and you've got this as an extra tool in your toolbox. Kramer's rule it had a purpose, right? You were trying to compute something. And we had other ways of computing that something. And so you could either memorize the formula and have a formula that you just pop out and throw some numbers in and something pops out on the other side, you don't have to think about it, right? Or you can use one of these other methods, which might require some more time and effort, or might not. And you get the same thing. Now I will say, the thing that Kramer's rule does compute, why am I talking around it? It's computing the inverse of a matrix, right? Or that's one of the main applications of it is computing the inverse of a matrix. You will have an opportunity to do that on the exam. So you will have an opportunity to use Kramer's rule, but you will have just as much opportunity to not use Kramer's rule.
So you're saying computing the inverse, whether or not we want to take that avenue?
Well, one thing I'm saying is computing inverses will be, knowing what an inverse is necessary. Computing what an inverse is very, very helpful. Using Kramer's rule to compute it is optional.
Okay, yeah, that's fine.
I'm not a big fan of the types of questions where you just spit out a definition or you spit out a formula and it's just like, can you memorize something? Can you do just as good what a piece of paper can do? A piece of paper can store the formula just as good as your memory can, or better. The paper doesn't forget. It's a lot less effort to get the formula on a piece of paper. So I'm not a fan of questions like that. I more appreciate questions where you have an opportunity to demonstrate reasoning. So that's what I like to put with using. How do you feel? Feel good?
I'm going to study tonight, so hopefully I'll feel better about it.
Yeah. I had this experience recently when I was studying something, and I kept feeling like I wasn't getting it, you know? And then later on, I was like, oh, okay, yeah, now I see it. There had to be a transition somewhere in between, right? And so there's this process of learning that happens even when it feels like it's not happening. So, I don't know. I thought that was kind of an encouraging thought. If you're doing, as long as you know you're doing the thing that causes you to learn, you can just trust the fact that it's happening, even if it doesn't feel like it's happening. That's education psychology. Okay, we gotta fill the time with something. You gotta ask questions. Somebody's gotta ask questions. Questions from the exams? Questions from stuff that we just talked about? What was the last thing we talked about?
Least squares.
Least squares, yes. That was the last thing that's the last thing that's gonna be on the exam.
Oh, I was going to ask, is there going to be any particular weight towards the things that haven't been covered in previous exams, or are we treating it all as equal, I guess?
What I tried to do was take questions that were from the recent material and break them down into pieces where you would apply the stuff that you had earlier. So the content of the